Greetings, I'm Squared here, and we are going to talk about finding the area of a segment of a circle. So it's kind of weird, a segment of a circle. It's because usually we think of segment as part of a line, but a segment of a circle is the part of the circle that is bound by a chord, the endpoints of a chord, and the edge of the circle. So it's this little shaded area right there. And the way you do that is you find the area of the sector. Remember, the sector is formed by two radii and the edge of the circle. That's the sector. So you find the area of all of that, and then you subtract the area of this triangle. Now you are definitely going to need a calculator for this because we're going to round to the nearest tenths like the book has wanted us to do. And this is the formula we're going to use. So we have to make sure we know what all these things mean. N is the central angle, and our central angle is going to be in degrees. Sometimes it's in radians. That's a different formula. We're just going to use degrees, so in this case, that's 120 is our central angle. R is the radius, so our let's just write it down. Our N is, our central angle is 120 degrees. Our radius is 12 centimeters. And our base and height, we don't know yet. We have to find that from that triangle. So this part is relatively easy. We have all of that information right now. So we could go ahead and find that. We could say 120 divided by 360 times pi times 12 centimeters squared. So we could say, oh, those are reduced by 10. 12 goes into there 3 times. I've got 1/3 times 144 pi centimeters squared. Now I have to subtract 1/2 the base times the height. That's what I'm looking for. So I like to draw this triangle as close to it looks as possible because I need to find the base and the height. Now I know that a central angle is equal to its intercepted arc. So although it's not telling me that that's 120, I know it's 120, just in case you're wondering how I knew that that was 120. So that's 120. I know that both of these are radii, and all radii in one circle are the same. So that's 12 centimeters. I've got to find this base and this height. Because it's an isosceles triangle, if I drop an altitude, which gives me a right triangle, two right triangles, then I've split this central angle in half. So it used to be 120, now each of them are 60. And that gives me a 30, 60, 90 triangle. So I can sing my little song and find out all those parts. So let me just draw this over here, because it got a little sloppy there. This is 60, this is 30, and I know this is 12. In my 30, 60, 90 triangle, remember, the hypotenuse, which is 12, is always twice as big as the shortest side. So I know that's 6. Over here, I know that that relationship is 6 radical 3. I multiply by 6 radical 3. If you didn't remember that, you could have sung the little song, 30, 60, 90, 1 root 3 and 2. And then we set up the ratios. So I would have said 12 is to 2 as, and I wouldn't have known that, so I would have called it x, as x is to 1. And then I get 2x equals 12, and I get 6. So you could do it that way, but it's easier, a little shortcut. So we got a lot to do, so I'm just going to give the shortcut. So now that I know this is 6, this is my height. So I go base times height. I'm going to put my height there. That was 6. And then I only found this much of the base. So remember, it's an isosceles triangle that I cut in half, right? So this would be the same. So I'd have 2 of those. So the whole thing, if this is 6 radical 3 and this is 6 radical 3, is going to be 12 radical 3. And now I'm ready to really use my calculator on this thing. Sometimes I simplify it a little bit more. Sometimes I just put the whole thing in my calculator. So for example, how many times does 3 go into 144? So I get 48 pi centimeters squared. This is also centimeters squared because this was centimeters and that was centimeters. I'm going to reduce that. 12 divided by 2 is 6. So I end up with 36 radical 3 centimeters squared. And I just put it in my calculator. So 48 times pi minus 36 times the square root of 3. And that is me 88.4426, but it said round to the nearest tenths. And do not forget you are finding area, put your units. Okay, so now all the ones I'm going to give you today are special triangles, but if it wasn't a special triangle, then you just use sine, cosine, and tangent, the ratio. you know, sine is the opposite over the hypotenuse, cosine is the adjacent over hypotenuse to find the side, and you'd find an approximation of that. Okay, so our central angle is 60. So we know it's 60 times over 360 times pi r squared, and our pi is 6, so we have 6 centimeters squared. That's the area of our sector. This cancels. This cancels. It looks like here we have 6 pi centimeters squared, because that would have been 6, and then divide. You can use your calculator if you don't trust me, but I'm pretty sure that's right. 1/2 the base times the height. I'm going to put the base here, the height here, but now I've got to find it. So I'm going to draw my triangle over here, make it a little bigger. That's a 60-degree triangle. This makes this an isosceles triangle. If you don't know that, then you'll have to figure that out on your own. But because I know that both radii are 6 and this is 60, so those two angles have to be equal, so that makes them all 60. But you could have figured it out, because that would have been 30 and then 60, and it would have been 30, 60, 90 triangle again. Hypotenuse, shortest side, 3. So you could have figured it out. Shortest side to longer side is 3 radical 3. So my height is 3 radical 3, but my base is 6. So this cancels. I get 3 there, so that's a 9 radical 3 for my area, centimeters squared, 6 pi centimeters squared. So I'm going to take my handy-dandy calculator, and I'm going to say 6 times pi minus 9 times the square root of 3, and that gets me 3.26, but since I'm rounding to the nearest tenths, I'm going to say 3.3 centimeters squared. Voila! One more. Okay, our last one for this video. So we've got a central angle of 90. So that reduces to 1/4. We've got a radius of 12 centimeters. We're going to square that. Pi r squared times n over 360. That's 1/4. And that's going to be 144 when we square it, centimeters squared. And 4 goes into 144 36 times. So this is going to get me 36. We have a pi. Don't forget our pi. 36 pi. That's our area of our sector. Now I have to subtract the area of our triangle, 1/2 the base times the height. So this is 90, but when I cut it in half, I get a 45, 90. So I'm going to put that, just that one part of the triangle. This is my radius. It's 12. That's this part. And now, because it's 45, 90, I know that those parts are the same. So I still have the other part of the base out here, so I'm just going to have to double it, right? Because that's the whole picture. But the relationship between these two sides is it's 1, 1, and root 2. So this one is always the square root of 2 bigger than that one. So to find out this side, I have to divide by the square root of 2. And the base and the height are the same here. So this is the 12 over square root of 2, 12 over the square root of 2. Now normally I'd tell you to get rid of the rats in the basement, but we're just going to solve to the nearest tenth, so we don't need to worry about that. We just need to know that there's 2 of them here. So if this is 12 squared, it's 12 over the square root of 2, and this is 12 over the square root of 2. If I have 12 of them here and 12 of them there, then the whole base is 24 over the square root of 2, and then the height is 12 over the square root of 2. So I'm going to multiply this out. So 24, I'm going to reduce here, 24 and 2. 24 divided by 2 is 12, so that's 144. And then root 2 times root 2 is root 4. The square root of 4 is 2, and that goes in 72 times, I believe. 144 divided by 2. So now we get our handy-dandy calculator out. We got 36 pi minus 72. We press enter, and we get 41.1. And what were our units here? Centimeters, so centimeters squared. And that, my friends, is how you find the area of a segment of a circle. How exciting is that? Good luck. M squared signing out.